SPIE presents the Advancing the Laser series, honoring 50 years of laser achievements.
I'm Frank Wise. I'm with the Department of Applied Physics at Cornell University. At the moment, we're very motivated to help our colleagues in biophysics and biomedical applications do their jobs. There are people who've come up with fantastic new ways to do microscopy, for example, and eventually working toward endoscopic applications for detection and eventually treatment of disease. Commercial femtosecond lasers now are absolutely fantastic tools for research labs. Okay? They're absolutely beautiful, they're incredibly reliable. They're somewhat expensive, about $100,000, but it's actually a good deal. But they're limited for going outside of research labs to some extent. And again, if we want to be able to put one in every microscopy facility or teaching lab, bioimaging facility, and eventually in clinics, we have colleagues who are working very hard to take new imaging techniques into clinics, and I'm always surprised when they tell me my Ti-Sapphire laser is great, but it will never work in a clinic. We need something better. This is a mode-locked laser that offers the performance almost of a femtosecond titanium sapphire laser. It doesn't have a pump laser attached to it, which would just be a device, a box about this big, okay, that sits over here. And by seeing it, you can see the potential. Okay, it's all fiber. It will be incredibly cheap to manufacture. It was stable, reliable, compact. Now, I should say that to get from a solid-state laser to the same performance in fiber, there are some major scientific challenges, and that's what attracts us. If this were just somehow engineering the same pulse propagation physics into a different package, we wouldn't be interested. Okay? It takes new concepts in pulse formation to actually make a stable pulse of very high energy that will propagate in fiber. And in this case, the laser cavity actually just is fiber spliced together. Light goes around the cavity, and then we splice on a pump laser and the light can come out. And so we now make lasers that don't have any anomalous dispersion in them. They're completely normal dispersion. The pulse goes around the cavity, always highly chirped inside the cavity, and then we dump it out, and then we can de-chirp it to the transform limit, the bandwidth limit of the pulse outside. Okay? So clearly it's not a soliton if it doesn't have any anomalous dispersion inside the cavity. It can't be an ordinary soliton. So what makes the pulse? The answer is we put a filter in the cavity. If a highly chirped pulse encounters a filter, the cutting off the edges of the spectrum is the same as cutting off the front and back of the pulse in time. So that's something that sharpens a pulse or promotes pulse formation. Okay? So the pulse in such a laser, we call these all normal dispersion lasers. The pulse in such a laser is a dissipative soliton, not an ordinary soliton. Dissipative refers to the system and the way it's produced, not to the pulse itself. The pulse itself is actually perfectly stable. Okay? And this was done by graduate students in my lab, Andy Chong and Will Renninger, a couple years ago. And we've since been figuring out how to optimize these, and it turns out this is, as far as we know, fundamentally the way to the highest pulse energies in a mode-locked laser. And as a result, we actually now have fiber lasers that are competing in our lab, that are competing head-on with a mode-locked laser like titanium sapphire. Now this is a first. We have the first fiber lasers to make several watts of average power and 100 femtosecond pulses. So we see now our next step is to take those lasers and to make them into all fiber format like this. And you can imagine if this can perform equally to a Ti-Sap, this is going to be able to have impact in a variety of applications. I don't envision lasers coming more into society and solving those big problems. What I do envision is lasers being critical to figuring out the science that's going to let us get solutions to those problems. Okay? And maybe I'm biased by the types of things we do, but I'll give you an example. We're currently working on making solar materials that could be valuable for solar cells, and they're based on nanostructures. Okay? So how do we do that? The first thing we have to understand is a very fundamental process. If we create electrons in a nanostructure, how do we get them out? How do we get them out efficiently? Because we want them to go to an electrode to make some energy, to make some current. So we use lasers, 10 different types of lasers, to study the properties of, for example, a nanocrystal attached to a metal oxide, to study the fundamental processes. We use ultrafast pulses to excite electrons and holes in the nanocrystals and then monitor the transfer of charge to other things. Okay? We use optical spectroscopies to study the properties of the nanocrystals themselves. So there's a huge amount of these. If this all works out really well, at some point in the future there will be nanocrystal-based solar cells, and I think these are very promising, but where the laser will have come in is in the underlying science, not in the actual application at the end. I think it's going to be huge in the impact that way, maybe less so in the more obvious or tangible application at the end. Okay? And of course, we can even go a step further. We're now using lasers to understand fundamental processes in nature and then try to exploit them in devices or applications. But people are thinking a step further. We can use light to control nature. We can possibly control individual atoms, individual molecules, individual nanostructures to make the processes happen that we want. Again, my view is that will lead us to deeper understanding, which will allow us to create structures that will be good for the applications.